In this video, we're starting section 2.5 on cardinality. So this has to do with how big infinite sets are, how many elements they have. So we're going to define the cardinality of infinite sets. That'll talk about how large they are. Define and give examples of countable and uncountable sets. And determine whether a set is countable or if it's uncountable. So in this video, we'll talk about Hilbert's infinite hotel and define cardinality for infinite sets. So here is the situation. Hilbert's hotel has an infinite number of rooms, numbered 1, 2, 3, and so on. And every room has a guest occupying it. So let's suppose that Lavrith shows up to Hilbert's hotel and asks for a room. Can the hotel manager find a room for him without having any guests leave the hotel? So we have this infinitely large hotel, an infinite number of rooms, but all of them are occupied. And now Lavrith, which is my name, so I'm going to draw me. So Lavrith shows up and asks for a room. Can the manager fit them in? Well, it turns out yes. And this is a little weird. But the way that they do this is they'll have whoever's in room number 1 go to room number 2. Whoever's in room 2 go to room 3. The person in room 3, they'll move to room 4. The person in room 4 go to room 5 and keep going like this forever. Keep going like this forever down the chain. Okay. And when that happens, everyone has a room to go to because it keeps going forever. There's an infinite number of rooms. So no two people are going to be in the same room. But by doing this, room 1 is now free for Lavrith. Room 1 is free. Is free for Lavrith by moving people around like this. So what we're doing is we're asking the person in room N to move to room N plus 1. So it's a little bit weird. This infinite hotel was full, but by shifting people around in this way, we were able to free up a spot for one extra person. So in some sense, like infinity and then adding 1 to it still is able to fit in the same infinitely large container. We can actually do this for any finite number of extra guests. Like, for example, if 7 new people showed up in this way, then the hotel manager would just ask the guest in room number N to move to room number N plus 7. So they'd shift everyone down 7 spots, and that would open up the first 7 rooms for these new people. Okay, so now let's make it a little more interesting. So let's suppose that a bus with an infinite number of passengers shows up to Hilbert's hotel, and all the passengers on the bus ask for rooms. Can the hotel manager find rooms for them? Ooh, so this seems tougher. We have this this bus with an infinite number of passengers. So I'm going to draw a picture. So imagine a bus. But imagine the bus. It's got to be an infinitely long bus. So I'll put ... So it just goes on forever. And the bus opens up its doors and out walk these infinitely many passengers. So passenger number 1 and passenger number 2 and passenger number 3. There are an infinite number of these passengers. Can we find rooms for all of these people? So now the shifting trick from the last one won't work because I'd have to shift each person like an infinitely far down, and it's not clear how far that person needs to move. But what I can do is the following. Let's ask the person in room number 1 to go to room number 2. So I'm doubling their room. Room number 2 to go to room number 4. So I'm doubling their room. Room number 3 to go to room number 6. So doubling theirs as well. And room number 4 to go to room number 8. So I'm going to ask the person in room number N to move to room number 2N. I'm doubling everybody's room. And by doing this, I'm going to highlight the rooms that open up. Everyone's going to move to an even numbered room. So all the odd ones will open up like 1 and 3 and 5 and 7. No one's moving into any of those. So by doing this, odd numbered rooms will open up. So we can fit these infinite number of passengers. So we can fit these infinite passengers. So that is weird. If a whole new set of infinitely many people shows up to a hotel that's already filled, we can somehow fit them in. So this is very weird. Okay, so what we've showed in a sense from part A is that the set that contains 1, 2, 3, and so on, positive integers, has the same size as if I were to include an extra element, which I'll just label as 0. Part B shows that if I had the positive integers, that has the same size as another set that contains all the positive integers that I had before, all the old guests. So all my guests, 1, 2, 3, comma, dot, dot, dot. But also now another infinite set of guests, which I will number as -1 and -2 and -3. Those in some sense have the same size. Okay, so let's make this more precise. Let us make this more precise now. So for example, in part A here, the reason why these two sets actually have the same size is if we list out their elements. So the elements in this new set are 0, 1, 2, 3, and so on. And the elements in this first set are 1, 2, 3, 4, and so on, 4, and so on. We can associate these elements in a one-to-one correspondence. So I can map 0 to 1 and vice versa, 1 to 2 and vice versa, 2 to 3, 3 to 4, and so on. This was my rule where I'm sending the person in room n to room n plus 1. So what we're doing is we're associating every element in this first set with exactly one element in the second set and vice versa. So more precisely, what we can say is that there's a bijection, a function that's both one-to-one and onto, that whose domain is these non-negative integers, that's the set I'm starting with, and whose codomain is the positive integers, that's this new set that I'm ending with. And the formula for that bijection is f of n equals n plus 1. We're sending the guest in room number n to room number n plus 1. So the fact that these sets are infinitely large opens up this possibility that I can do this even if at first glance it seems like these sets have different sizes. So we're ready to define cardinality. We say that A and B, two sets, have the same cardinality if and only if there's a bijection from, between the two sets. And if there is a bijection, the way I write cardinality is I put my set and I put absolute value bars around it. That's the cardinality of A. So we say that cardinality of A is equal to the cardinality of B. When my sets are finite, they would have the same cardinality if and only if they have the same number of elements. Okay, so for finite sets, cardinality is kind of what we'd expect. But for infinite sets, weird things can happen. There are clever ways that we can form these one-to-one correspondences. Or in terms of my hotel, clever ways that we can sort of adjust these guests around to fit other things into our set. Okay, so this is what we're going to explore a lot more in detail over the course of this section, the sizes of infinite sets.